These should be familiar. They're what we call, of course, the circumference and area formulas for a circle. Have you ever noticed that the derivative of the area formula is actually the circumference formula? The derivative of the area formula with respect to r. Take the derivative of r squared. Pi is just a constant. Derivative of r squared is 2r, so you get 2 pi r. The derivative of the area formula for the circle is the circumference. Is that just a strange coincidence? Well, here's a couple of formulas you may be less familiar with, but you've probably seen them before. For a sphere, the surface area is 4 pi r squared. The volume is 4/3 pi r cubed. And look again, the derivative of the volume, well, the derivative of r cubed is 3r squared. The 3 cancels out this 3, 4 pi r squared. It's the surface area. The derivative of the volume of a sphere with respect to the radius is the surface area. That makes you think that there must be something going on here. It can't just be a complete coincidence. So let's see if we can prove that the derivative of the area of a circle is in fact the circumference. So let's start off with a circle of radius r. And the first thing we ought to say is, well, the derivative is a rate of change. So what's changing in a circle? Well, you got to think about it as suppose the radius grows. The question is, how fast does the area grow compared to the radius growing? That's when we're talking about the derivative of the area with respect to the radius. So let's grow the radius a little bit. A certain amount, delta r, you're familiar with that. Delta is a change in r. And of course, we're thinking of delta r as being a very small amount. I've made it bigger so we can see it. So by extending r a little bit, we've increased the area of the circle by this ring, this green ring that we have out here. And the question is, what's the area of that ring? How big is it? And how does it compare to the length of the radius that we added? So the change in the area is the green part, the area of the outer ring. And what I want to claim is that it's roughly equal to the circumference of the circle times this change in the radius. Now let's think about that for a second. The circumference of the circle times the change in the radius. If I had a rectangle that had a length of the circumference and had a height of delta r, then that rectangle would have area c times delta r. So what I appear to be saying here is if I took this green ring and I cut it, say over here at the bottom, and I straighten it all out, then I would have a rectangle whose width or length is the circumference of the circle and whose height is delta r. So is the area of that rectangle the same as the area of this ring? Well, let's look at that a little more closely. Let's take a blow up of this ring. And what I'm going to do is I'm going to embed a few squares in it. Now you can imagine it's going on further, but I've embedded these few squares. And if I just take this part of the ring and straighten it out, what happens? Straighten it out. Well, the area contained in all these squares is contained in the rectangle that I got by straightening out. But look what's missing. All the area between the squares is missing. So when I'm trying to say that the area of the ring is kind of equal to the circumference times delta r, it seems like I'm missing a lot. But look, I said it's approximately equal. And I also said that you should be thinking of delta r as very, very small because we're talking about the instantaneous rate of change. So let's slim this thing down. Let's cut the ring into something much smaller. So delta r is much smaller. And now again, we're going to put some squares in there, but it's going to be hard to see them if we don't focus our attention on a small area. So let's focus on that and blow it up a little bit. Now I'm not going to draw the squares, but picture them yourself here. So I draw a square and another square. Now look at these squares. This thing is not bent nearly as much as the first picture. So when I straighten this out, yeah, I'm going to lose a little area between the squares, but not very much. And then imagine for yourself that I cut this down even more. I make the ring very skinny, and I put squares in that. And again, I'm going to have to focus on a very small portion to even see those squares. And look, that portion is practically straight. I'm not going to lose any area, hardly at all. So what we're saying is that in the long run, if the delta r is small enough, if the change in the radius is small enough, then the area of this very skinny ring is going to be very close to c times delta r, the circumference of the circle times the change in the radius. So delta a is roughly equal to c times delta r. So what we're looking for is the comparison, the change in the area compared to the change in the radius. That's roughly c. And as we just said, this approximation gets better and better. The closer delta r gets to 0, the smaller delta r gets. So that means the derivative of a with respect to r is exactly the circumference, which is what we said in the first place. And notice that we didn't even use pi at all. This was just strictly from the geometry of the circle. So what we're actually saying here is that the instantaneous rate of change of the area compared to the radius is the circumference, or said another way, the additional area added to a circle per unit of additional radius is the circumference. Now, does that seem a little funny? I mean, area is kind of a square thing. We're saying the additional area is the circumference, which is a linear thing. But be careful. We're not actually saying the additional area. We're saying the additional area added to a circle per unit of additional radius. So it's area divided by a linear amount, the radius. And that, as you should expect, is a linear amount, the circumference. So what that enables us to do is to think of the circle in a very special way. If you picture the radius growing a little by little, tiny, tiny little bit of radius, what you're doing is adding a circumference at that particular moment. So you can think of the circle as being built up of these circumferences. You start out with a very small circle. It's got a circumference. You make the radius a little bigger. You get a circumference wrapped around that and another circumference wrapped around that. So think of the circle as made up of longer and longer, extremely thin pieces of string, the circumferences, all wrapped concentrically around each other. Now, we'll find it's very profitable to think about the circle this way when we want to think about how big the area of a circle is. That is, we want to think about the area formula that we showed in the first place. We'll do that next.